Case study: enhancing cybersecurity with AI-powered intrusion detection systems, a cross-sector perspective. The financial sector has always been a prime target for cyber attacks, given the sensitive nature of the data it handles. In one instance, a large financial institution faced a persistent problem with cyber threats that had the potential to cause significant financial loss and reputational damage. The institution decided to implement a sophisticated intrusion detection system powered by artificial intelligence to bolster their cybersecurity defenses. This IDS leveraged both supervised and unsupervised machine learning techniques to enhance its detection and response capabilities. Supervised learning algorithms were trained on labeled datasets comprising known attack patterns and benign network traffic. This training allowed the system to develop a nuanced understanding of typical and atypical behaviors, enabling it to accurately flag known threats. However, the financial institution recognized that relying solely on supervised learning could leave them vulnerable to zero-day exploits and previously unknown attack vectors. To combat this, they integrated unsupervised learning algorithms into their IDS to detect anomalies in real-time network traffic. These algorithms could identify deviations from normal patterns, thereby spotting potential threats that had not been seen before. This dual approach proved immensely successful. The institution saw a substantial reduction in the time required to detect and respond to cyber threats, enhancing their overall security posture. But what are the specific advantages and challenges associated with using supervised versus unsupervised learning in IDS? Supervised learning excels in identifying known threats with high precision, but can struggle with new or evolving threats. On the other hand, unsupervised learning can detect novel threats, but may also generate more false positives. How can an organization balance these trade-offs to maximize their security? Another compelling case involved the application of AI in cloud computing environments. A cloud service provider hosting vast amounts of data faced an increasing number of cyber attacks. The provider adopted deep learning techniques, particularly convolutional neural networks, to enhance their IDS. The CNN-based IDS analyzed network traffic data to identify subtle deviations indicative of malicious activity. In one study, the CNN-based IDS achieved an accuracy rate of 98.7% in detecting distributed denial-of-service attacks, significantly outperforming traditional IDS methods. What makes deep learning especially effective in such settings? Deep learning techniques excel at processing and analyzing large volumes of data, making them ideal for dynamic and complex environments like cloud computing. However, they require substantial computational resources and large datasets for training. How can cloud service providers ensure they have enough high-quality data for effective deep learning model training? One approach is to leverage federated learning, which allows models to be trained across multiple decentralized devices or servers holding local data samples without exchanging them. This method enhances the scalability and efficiency of AI-driven IDS, enabling real-time threat detection and response across distributed networks. The healthcare sector also offers a pertinent example. A large healthcare provider network, handling highly valuable medical records and personal health information, implemented an AI-driven IDS using a hybrid approach. This system combined rule-based systems with machine learning algorithms. The rule-based component was designed to detect known threats based on predefined signatures and patterns, while the machine learning component focused on identifying anomalies and potential threats not covered by the rule-based system. This hybrid IDS was able to detect 96% of known threats and 92% of unknown threats, demonstrating the effectiveness of integrating traditional methods with AI-driven techniques. Yet, integrating rule-based systems with machine learning poses its challenges. Rule-based systems are limited to detecting known threats, while machine learning models can identify new threats but may require continuous learning and adaptation. What strategies can healthcare organizations employ to maintain the efficacy of such hybrid systems? Continuous monitoring and updating of rule sets, along with periodic retraining of machine learning models on new data, can help maintain their effectiveness. Moreover, The use of explainable AI techniques can enhance transparency and interpretability, helping cybersecurity professionals understand and act on the outputs of AI systems. Critical infrastructure protection is another area where AI-driven IDS has proven invaluable. A smart grid environment faced sophisticated cyber attacks targeting its power distribution systems. To counter this, an AI-driven IDS utilizing a combination of support vector machines and genetic algorithms was implemented. This system analyzed network traffic to detect anomalies indicative of cyber attacks, achieving a detection accuracy of 95% and significantly reducing the false positive rate compared to traditional IDS methods. What are the primary benefits and limitations of using SVM and genetic algorithms in IDS for critical infrastructure? SVMs are effective in high-dimensional spaces and can handle large datasets well, making them suitable for complex environments like smart grids. Genetic algorithms, inspired by natural selection, are excellent for optimization problems, helping to refine detection models. However, both techniques require careful tuning and significant computational power. How can organizations ensure the optimal performance of these algorithms? Regular performance evaluations, parameter tuning, and incorporating feedback loops for continuous improvement can help maintain their effectiveness. The integration of AI into IDS is not without its challenges. One primary challenge is the need for large and diverse datasets to train machine learning models effectively. The performance of AI-driven IDS is heavily dependent on the quality and representativeness of the training data. Inadequate or biased datasets can lead to poor detection accuracy and high false positive rates. Additionally, the dynamic nature of cyber threats necessitates continuous updating and retraining of AI models to maintain their effectiveness. Despite these challenges, the benefits of AI-driven IDS in terms of improved detection capabilities and reduced response times are undeniable. How can organizations overcome the challenge of acquiring quality datasets? Collaborations and data sharing initiatives among organizations within the same industry can help create comprehensive datasets. Moreover, synthetic data generation techniques can be employed to augment limited real-world data. As AI technologies continue to evolve, advancements in explainable AI are expected to provide greater transparency and interpretability of AI-driven IDS decisions. This is crucial for building trust and ensuring that cybersecurity professionals can understand and act on the system's outputs. Ongoing research and development in areas like federated learning and edge computing are expected to further enhance the scalability and efficiency of AI-driven IDS. Federated learning enables real-time threat detection and response across distributed networks without the need for centralized data collection. Edge computing brings computation closer to the data source, reducing latency and improving response times. These advancements will play a pivotal role in the future of AI-driven IDS, providing robust protection against an ever-increasing array of cyber threats. In summary, the application of AI in intrusion detection systems has proven to be transformative in the field of cybersecurity. The case studies across different sectors highlight the significant advantages of AI-driven IDS in terms of improved detection accuracy, reduced response times, and enhanced overall security. The challenges associated with AI integration, such as the need for quality datasets and continuous model updates, are being actively addressed through ongoing research and development. As AI technologies continue to evolve, the capabilities of IDS will undoubtedly be further enhanced, providing robust protection against an ever-increasing array of cyber threats.